I'm Mr. Bremberger.
Today we have a video for you about static electricity. So first, we just want to start out by looking at a couple pictures. Wondering if you've ever had any of these problems. So especially as winter comes, you usually will experience something like this, very staticky hair. We have getting shocked by a doorknob, and then also clothes sticking to each other when they come out of the dryer. So we'll kind of explore some of those things throughout the unit, and you'll soon know why these things happen the way that they do.
So, we'll dive right into the types of charge. A little bit of review for you. As far as charge and their interactions go, remember those protons within an atom, they're tightly bound to the nucleus, and which means they really can't go anywhere. So when you put a proton by a proton, those like charges are going to repel. Electrons, though, on the other hand, we can transfer these around from one object to another because they are not as tightly bound to that nucleus. And when we do have electrons interact with one another, they tend to repel as well. Just like the positive and positive will move away from each other, the negative and negative will move away as well. Which means your positive and your negative, your opposites here will attract. Now recall the electric field hockey. We did a lot of charge interaction within that particular activity. So that would be a good thing to kind of hopefully recharge your memory with respect to charges.
Alright, so this unit is about static electricity, which is the buildup of charges on an object. In other words, those electrons that we're going to be focusing on, because those are the ones that we can transfer from object to object. So here's a question. Why aren't you attracted to or repelled by every object around you if all of our atoms are made up of these different electric charges? The answer to that is that each atom has the same number of protons and electrons. So everything around you, including ourselves, we are balanced or neutral. If we have the same number of positives and negatives, they just cancel out. So if we want to look at something like static electricity, we need to think about how do charges build up on other objects? How do those electrons get moved around and charge something up? And there's three ways that we're going to look at: friction, conduction, and induction. So let's take a closer look.
All right, our first type of charge transfer is totally based on friction, all right, which is the transfer of charge by rubbing two objects together. Here you see a young lady that took a couple of balloons and rubbed them against her head. In doing that, what she was actually doing is taking the electrons that are in her hair and placing them onto the balloon. So, essentially we're adding more negative charge to each of these balloons, which causes them to stick together with her hair, which becomes a little bit more positively charged. Remember that law of conservation of charge. We can't kill the charge, all right? We can't destroy it either, which means we're simply going to pass it from one object to another, and friction is one way of doing that.
Alright, our second way that charge can be transferred is through conduction. So looking at the definition, conduction is the transfer of electrons from a charged object to another object, this time by direct contact, so just two things touching. Not like friction where they have to be rubbing together, but just direct contact. So here is an example of a young lady with a Van de Graaff generator, and she is directly touching the top of this. We have a couple of these, so we'll be doing a few labs in class where you'll get to work with some of these. And you may have seen them at museums and things before if you've been whenever you were younger. So here she is directly touching the top of the Van de Graaff generator, and the electrons inside are transferring to her, creating this static electricity in her hair.
All right, the third and final type of charge transfer is known as induction. Now, I think of the three, this might be one of the more difficult ones to kind of grasp, because we're not touching objects together, without rubbing objects together. Here we're actually going to move charge based on the charge of something else. So if you think about the balloon that we charged up before, by rubbing against a piece of wool or your hair, again, we're going to place those negatively charged electrons on that object. The addition to this experiment here is we're bringing in a Cheerio, which has a neutral charge. So if we go through and add up the pluses and the minuses, the protons and the electrons, they're going to equal one another. Now, if we move that if we move that neutrally charged object near the negatively charged one, we can get those electrons on the balloon to kind of gather in one spot, which will draw this Cheerio closer to it, or actually kind of attract it in there because of the difference in charge. So again, induction is the movement of electrons by one part of an object caused by the electric field of another object.
Alright, our last big concept that we're going to talk about today is static discharge. So if we're going to have all of these charges building up in a certain object, either through friction, conduction, or induction, at some point those static charges need to leave and bring whatever that object is back into balance, back to neutral. And that is what happens during static discharge. So this is the loss of static electricity as electric charges move off of an object. So when you touch a doorknob and you're feeling that shock, all of the electric charges that have built up in you, maybe from rubbing your socks on the carpet, are leaving you and going into that less charged doorknob, creating this more neutral state for both objects.
All right, please remember, as part of activity 3, take a moment and go and complete the form. Actually, I'm sorry, part of activity 2, complete the form, and then obviously move on to activity number 3 of our unit guide.
All right, thank you.